Hello there and welcome. This is the second video from section 5.1. We're going to be estimating the area under a curve using rectangle approximations. This is just a follow-up from the previous video, which was using rate data to estimate a quantity. If you haven't checked out that previous video, you might want to look it over just briefly because this method is just an extension of what we did in the previous video. All right, so let me show you how to estimate the area under a curve with a couple of examples. All right, so our first example here, we are given a function y equals 42 over x, and we're asked to find or approximate the area between the x-axis and this function, and it does give a very specific domain, so between 1 and 7. Let's get an idea of visually what that looks like. So on Desmos, I graphed this function, and I restricted the domain from 1 to 7. So that's this function right here. You can see when x equals 1, the y value is 42. That's because 42 divided by 1 would be the y value of 42. And at the other endpoint, we have x equals 7, and that corresponds to a y value of 6 because 42 divided by 7 is equal to 6. And we're looking for the area under this curve and above the x-axis. I'm going to go back to annotate and to our lecture notes, and I'll just draw a brief sketch of this so I can show you what's going on. So we have this thing, and we started with 1, and we ended up at 7, and we had started with a y value of 42, ended up with a y value of 6. And this is not to scale, sorry about that, but I'm just trying to get a rough sketch here of what's going on. All right, so the idea is we're going to be trying to find the area under the curve and above the x-axis. So that would be this area right here. That's under the curve and above the x-axis between x equals 1 and x equals 7. And the way we're going to be doing that is we're going to be breaking up this region into rectangles. So we're going to be sort of looking at this and saying, okay, well, let's just look at some rectangles. And each time we draw a rectangle, we're probably not going to get the exact area, but we're going to get something which approximates the area. If we make more rectangles, more and more rectangles, then it's going to be true that the leftover or the extra area, the area that's wrong, is going to be less and less and less. So making really small rectangles, you can see that I'm ending up with less error. We're not going to go into that level of detail at this point. I'm just going to show you how to find the area or approximate the area using rectangles. And then in a later section, we'll get a little more sophisticated with like how do we minimize this area? How can we find the exact area? That kind of thing. Okay, this does actually say use 3 rectangles and then use 6 rectangles. So we're going to do this problem twice. First, we're going to use 3 rectangles, and then we're going to use 6 rectangles as just a second version of the same problem. So we're going to break this into 3 rectangles, and we have 1 to 7. So we have to kind of think about what to do. Now, generally, we want to break them up into even sections, like even x-axis distances. So I think if I do 1 to 3, 3 to 5, and 5 to 7, that will give me 3 rectangles. So one rectangle between 1 and 3, another rectangle between 3 and 5, and the last rectangle between 5 and 7. In the previous video, we did these approximations, and we talked about an upper estimate and a lower estimate. We don't exactly do that in this version. We just do left-hand estimate and right-hand estimate. It ends up being a very similar thing. So what do I mean by a left-hand estimate and a right-hand estimate? So left estimate, and we will do a right estimate as well. So let me first do the left estimate. So in our rectangle, our first rectangle is between 1 and 3. It goes up to here for 1, and 3 goes up to here. And of course, it doesn't make a rectangle. We can approximate it using the left-hand endpoint as the height of the rectangle, or we could approximate this using the left-hand endpoint as the rectangle, right? So one of them, the left-hand endpoint estimate, would be actually creating areas which are larger than what we want. And the right-hand estimate in this particular example would be creating a rectangle with an area lower than we want. It's missing this stuff up here before we had too much stuff. So that's what we mean by left-hand estimate and right-hand estimate. So left-hand estimate for this first thing, we have to figure out this height here and figure out the area of that rectangle. In the second rectangle, it's from 3 to 5. 3 is right here. 5 is right here. These are the y values. I'm going to be choosing the left-hand y value to make my height. So I go over from the left-hand y value and down. So that's my second rectangle. The last rectangle goes from 5 to 7. This is the endpoint at 7. This is the endpoint at 5. Once again, I choose of these two like endpoints here, 5 and 7, I choose the left-hand one to make the height of the rectangle. And then I go down. So I'm going to find the area of these three rectangles and add them together. And that will be my approximation for the area between the x-axis and the function from x equals 1 to x equals 7. Now, we're going to turn this into a problem that looks like the last one we did. Last one we had tables of values. And based on the table, it was really easy to spot what the area was. So back to Desmos. Here's my function, and I actually made a table out of it. And here are the values, the little intervals that we broke up. 1 to 3 is our first rectangle, and you can see the left-hand endpoint is 42. And then from 3 to 5, that's our next interval, left-hand endpoint being 14, and 5 to 7, the left-hand endpoint is 8.4. And that creates this right here. To find the area, I just multiply the y times the x. The first rectangle goes from 1 to 3. So the x distance is 2. And the y distance, the left-hand endpoint is 42. So that's where I have 42 times 2. That's the width of the rectangle from 1 to 3 times the height of the rectangle. And we're using the left-hand endpoint. So it's 42. The next rectangle goes from 3 to 5. And the left-hand endpoint is 14. So that's why we have this right here. And likewise, the left-hand endpoint of the third rectangle times its width, 2, is 8.4 times 2. And so we have an approximation of 128.8 using the left-hand endpoints. The way your textbook author does this is they notice that there's a 2 in each of these terms because the width of each rectangle is always the same, always 2. And so they factor it out and they write 2 times, and these are the different y values. Now, personally, I think that's a little confusing when you're first learning about this. For many students, I believe just seeing that it's just length times width, it's just the x times the y, kind of makes more sense. But you will see this a lot because the math people like to factor stuff. For the right-hand endpoints, I'm going to be doing the exact same rectangles from 1 to 3. That's an x distance of 2. And I use the right-hand endpoint, which is 14. That's why I have 14 times 2. And likewise, the second interval has an x distance of 2, and the right-hand endpoint is 8.4. And the final one, the right-hand endpoint is 6. And so we get a right estimate of 56.8. In this particular case, the left-hand endpoint overestimates the area, and the right-hand endpoint underestimates the area. That won't always be the case, but in this case, it certainly is. And you could do something cheeky like average them together if you want an even better estimate. You really don't have to worry about that too much because we're going to learn some pretty sophisticated ways of getting excellent approximations without having to worry about averaging these kinds of things together. So just maybe for fun more than for actual profit of what we're going to be doing. Okay, so that is the idea behind this first one here. I can write down a lot of stuff here, but I'm not sure if that's really going to help folks. We have 2 times the y height here of 42, and then we have 2 times the y height of here, which is 42 divided by 3. 42 divided by 3, I guess, is 14. And then the next rectangle here from 5 to 7, we have 42 divided by 5, which I believe was 8.4. And then we add all this together, and we get whatever Desmos has. And the right-hand estimate will be the same, but we're using the right-hand endpoints instead of the left-hand endpoints. Right? And I'll just write down the numbers just so that they're on these lecture notes for people to review. So left-hand endpoint was 128.8, and the other one was 56.8. All right, so that's approximating using 3 rectangles. It also asks us to approximate using 6 rectangles. So now we're going to use more rectangles. That means we need to break the x-axis down into smaller segments. From 1 to 3, 3 to 5, 5 to 7. From 1 to 7 here creates only 3 rectangles if we're going by 2 each time. So if we want to get 6 rectangles, we're going to have to make a smaller distance in the x direction. And the way I set it up is if you just go by 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, it actually does make 6 rectangles. So 1, 2, 3, 4, 5, 6. I know there's 7 lines, right? You're counting lines, 1, 2, 3, 4, 5, 6, 7, but we're not really counting lines, we're counting rectangles. So here's the first rectangle between 1 and 2. Maybe let me put a 1 there or something, right? Here's the first rectangle between 1 and 2. Here's the second rectangle between 2 and 3. And then if you just count the rectangles, which is the spaces in between, you will see 6 rectangles. So there is kind of a nice way to know, like if they want 6 rectangles or 9 rectangles or whatever, like how far to go in the x direction. So we need to know the distance from 1 to 7 or from 2 to 10 or whatever makes a difference. The distance from 1 to 7 is 6 because I can just subtract 7 minus 1 to find the distance. So we're going to do the distance, which is subtracting these two numbers. 7 minus 1 is equal to 6. And then we need to divide by the number of rectangles. We have the distance of 6. And if we divide by 3, 6 is our distance divided by 3 rectangles gave us 2. That was what we did on the first problem when we had 3 rectangles. This is called our delta x. This is our change in x. If our distance was 6, and we want, this is rectangles, and we want 6 rectangles, 6 divided by 6 is equal to 1, which means our spacing is 1. The way we find distance is you just subtract the 2 endpoints. So in your textbook, you will see the formula where you take the 2 endpoints and you subtract them. And then you divide by the number and the number of rectangles. And that will give you the spacing in the x direction. So you'll see this little formula. If you want to use a formula, great. You just find the distance you want to go, divide by the number of rectangles, and that will tell you how far to go in the x direction each time. So in this case, we need to go 1 in the x direction each time, and that's going to give us 6 rectangles. So I've also prepared this ahead of time in Desmos. So here is the same function. Let me turn this off here. So here's the same function down here. But now I've made the dots go every 1, right? So at 1, at 2, at 3, at 4, etc. Right? So we have these 7 dots, these 7 locations, creating 6 rectangles. And in the first one, between 1 and 2, we take the left-hand endpoint for our left estimate and the right-hand endpoint for our right estimate. So that's what this represents. This is the left-hand endpoint 42 times 1. That's the left-hand endpoint between 1 and 2. So here's the 1 to 2 rectangle, and the left endpoint is 42, and the right endpoint is 21. So you can see that I have here 42 times a width of 1. From 1 to 2 is a width of 1 versus 21 times a width of 1. Left-hand endpoint, 42 times 1. Right-hand endpoint, 21 times 1. It is times 1 because the distance from 1 and 2 is just 1. It's no longer a distance of 2. So make sure you remind yourself to check the distance in the x direction for each rectangle. Second rectangle goes from 2 to 3. So again, an x distance of 1. Left-hand endpoint being 21. Right-hand endpoint being 14. So you'll see a 21 using the left-hand endpoint and a 14 using the right-hand endpoint. And I just continued that process for all of the 6 rectangles on the left and the right. So you can see those numbers matching up. And Desmos gave me the left-hand endpoint estimate and the right-hand endpoint estimate. And that's kind of what we want you to be able to do at this level in section 5.1 is just sort of understand what we're doing with drawing rectangles and calculating an area approximation. All right, I don't think I'm gonna write all this down on the lecture notes. Hopefully you can write it down if you'd like it on the lecture notes, or you can let me know and I'll help you transfer it over. All right, so that's the idea behind this. I have one additional problem. It's not much variation here, so I have an additional problem that's kind of similar. It does have a different function. So this function is y equals x squared over 2. I did give it a slightly different domain. So this goes from 0 to 8. And once again, we're trying to find the area or approximate the area. But this time we're going to be using 4 rectangles. So here's a great time to pause the video and give this a try. See if you can come up with left-hand endpoint and or right-hand endpoint estimates for the area. I'm going to pause the video, write up my solution, and then I'll come back and show you what I got. And you can compare your answer to mine. All right. Okay, so welcome back. If you gave that a try, great. This particular function goes up. It's kind of like a parabola. I guess it is a parabola. And if you got the first, the left-hand endpoint, the first left endpoint actually has a y value of 0. So the first rectangle, sometimes it confuses people. It has the left endpoint of 0 and a width of 2. So the first rectangle actually has 0 area in it because it's the left-hand endpoint, a left-hand y value times the x distance, so 0 times 2. And we carry through. Let me show you what it looks like on Desmos. I did actually draw this function from 0 to 8. And then I made a table from 0 to 8 counting by 2s. And here's my calculations on the left-hand endpoints and the right-hand endpoints and what I got for those. By the way, if you did use the formula, you would have done like b minus a over n is the change in the x direction. Our a and b values go from 0 to 8. That's our endpoints. So I would do 8 minus 0. And they total specifically 4 rectangles. So I did 8 minus 0 divided by the number of rectangles 4. And that's how far I go in the x direction, which in this case, 8 minus 0 divided by 4 is 2. So I know to go 2 in the x direction each time, 0 to 2, 2 to 4, etc. Right? So that's a way of knowing like how to break up your interval into even segments by doing something like that. All right, so that's it for this video on estimating the area under a curve using rectangle approximations. Please reach out if you have any questions or need help with anything, and I hope you have an enjoyable day.